I'll start this recording. Here we go. So you got a formula sheet, and so you'll get, I'll print new copies for the tests, and so they'll look the same. Well, they might print ugly like those ones, but they'll have the same information on them. And now you know when you're studying what you'll have and what you won't have, right? And so let's have a look at that probability section on your formula sheet. I highlighted some stuff, but just as a review, let's snag this part of your formula sheet. So we started probability last day. And as kind of a review, sort of, we'll use the probability section of your formula sheet. And so there are some general rules that all probabilities follow, right? And so any probability has to be between 0 and 1, right? So it has to be a proportion, right? Some decimal. And so we saw that pretty early on last week, right? We said, okay, probabilities have to be between 0 and 1, making them a proportion, right? So for that reason, a proportion is a probability. Oh, that's very annoying today. Use some formula sheets, maybe. More. All of them. All of them, so I can forget them there. Okay. So a proportion is a probability, right? And so those two P's go together. But then we also made the link that, okay, well, I can take a proportion, 0.6, for example, and our brains just automatically convert it to 60%, right, by multiplying by 100. And so then roughly a percentage, right? Not exactly equal, just because you have to multiply by 100, but all those three P's, you can use those interchangeably. So in this section, we're going to have questions that ask for what percentage of blah, 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 blah. What's the probability of this? What's the proportion of this? And those are all asking the same type of question. We introduced the idea of the sample space S. I'm not sure we called, I can't remember, we'll see on the next page, but S is the sample space, which is the set of all possible outcomes. The probability that something of all possible outcomes happens is 1, right? Which also means that the sum of all the possible probabilities has to be 1. Right? We also introduced the complement of A, which is the not A, right? And we said, okay, if I have the complement of A, so A to the power of C, that's the same thing as 1 minus A, or 1 minus P of A, because we'll be talking about the probabilities. Right? From here, right, we talked about probability distributions. What does it mean to have a valid probability distribution, right? And so we said, okay, I have to have a list of disjoint outcomes. Disjoint meaning there's no overlap, right? They can never happen at the same time, right? So I flip a coin, the result is either heads or tails. They can't happen at the same time, right? And then each of the probabilities listed in the probability distribution has to be between 0 and 1, and they have to add to 1, right? Otherwise, you haven't listed all the possible outcomes. And then the complement is just the probability of it not happening, right? we talked about the addition rule for two events, A or B, and we introduced it by looking at a deck of cards, right? We had a deck of cards and we said, okay, if I want to know the probability of a face card or a diamond, right? We can say, okay, I know the probability of a face card. There are 12 of those in a deck. And the probability of a diamond, there's 13 of those in a deck, right? So 12 over 52 plus 13 over 52. But then we saw we had to subtract the overlap, right? Which is the probability of A and B, face card and a diamond in this brief example, right? Which is 3 over 52. Right? And so for these, we said, okay, it might be easiest to see with a Venn diagram. Which means you have two circles here, and A and B is this shared space, right? You have to subtract that overlap, otherwise you're double counting. Today, well, I guess I already used, let me just change this to, gonna change it. I like to use pink for like new important things. So we'll use orange, orangey glad. There. These two sections we're going to see today. However, this one we saw last day. If A and B are independent events, then mathematically, what that looks like is that the probability of A and B is the probability of A times the probability of B, right? And so instead of saying, oh, these two things are independent, therefore I can use this, how I like to phrase this is if I give you each of these three probabilities, right? I give you the probability of A and B, I give you the probability of A, and I give you the probability of B, then if you multiply the probability of A times the probability of B, and you find that it becomes the same thing, the exact same thing as the probability of A and B, then they are independent. So here, I'll say given the probability of A and B, the probability of A, and the probability of B, we can show that A and B are independent events, right? We can show A and B are independent events if the probability of A and B is equal to the probability of A times the probability of B. They must be exactly equal. What does it mean to be independent? We just talked about disjoint. Disjoint means that there's no overlap, no outcomes in common, right? Whereas independence has to do with, I'll write this down because it can be confusing. Disjoint has to do with the outcomes, right? And so no overlap. Outcomes, right? A and B can't happen at the same time. What does that look like? It means the probability of A and B is 0. Whereas independence, right? If A is independent of B, then the probability of, or knowing that B happened has no effect on the probability that A happened, right? Whereas independence, if the outcome of A has no effect on the probability of B, so if knowing the outcome of A doesn't change the probability of B, for example, what we saw was, okay, I can flip a coin. Flipping a coin is a series of independent events, because knowing that I've flipped 10 heads already doesn't change the probability of flipping heads again, right? It's still 0.5. So independence is about the probability, right? As opposed to the possible outcomes. Okay. So today, like I said, we're going to talk about dependent events or conditional probabilities, which you'll see if we look at this line here. You don't actually need this bit, right? Why? Because you can rearrange the probability of A and B divided by the probability of B is the probability of A given B. We haven't talked about that yet, so I'll save it. But you only really need this one line here. Okay. So, any questions about that pretty intense review before we? There was a question where this is from continued from last week, and I can't remember. Oh, that's what we were doing. Okay. We were talking about uninsured Texans, I guess. And so if we are talking about whether you have health insurance or you don't have health insurance, right, then if we take a random sample of 5 Texans, which is kind of fun to think about, then the number of uninsured, right, the possible outcomes that we could have include 0, right? All of them could have insurance. That's perfectly reasonable, right? And so you don't want to forget about this 0 option, right? Flipping 0 heads is always an option, right? No matter how many times you flip a coin. And then of course you could have 1, 2, 3, 4, 5 insured or uninsured Texans, right, in a sample of 5. And we want to find the instances where at least one person is uninsured. Now, what you could find is you could find the probability that 1 is uninsured plus the probability that 2 is uninsured, or 3 or 4 or 5. And whenever you're saying or, you're adding, right? You're adding those probabilities. Or I guess I should say alternatively, what you could do is you could say, well, I know that the total probabilities here have to add to 1, right? From our formula sheet, we know that the probability of the sample space has to be 1. Right? One of those things has to happen. Okay? So then what can I do? I can say, okay, what if I find the probability of 0, right? And I just subtract the probability of 0 from 1. Oops, I thought it was in pointer mode here. Right? And that would save me a lot of work. I don't have to find the probability of 1, probability of 2, 3, 4, 5, and then add those all up, right? That's going to be the same as, what are we using? the complement, right? Not at least one is 0. Okay? So 1 minus the probability of 0 uninsured Texans. So we use this quite a bit where we know that the probability, the total probabilities have to add to 1, right? If I've taken everything into account in my sample space, it has to add to 1. So then the probability that at least 1 is uninsured is 1 minus the probability that none of them are uninsured. And so this is using the complement. Oops, complement. I'm going to have to assume that the probability of them being insured was 25.5% or 0.255. I deleted the slide, so I can't be sure, but let's say that's what it is. And so then the probability of being uninsured is 1 minus that, again, using the complement, right? And so then none uninsured. Oh, I see. Never mind. 1, 2, 3, 4, 5 Texans. Texan number 1, 2, 3, 4, 5. If the probability, let's see, of being uninsured is 0.255, then if this one has to be insured, and by the complement, the probability that they are insured, I feel like I made done a little switcheroo where that slide would be super helpful. Let me just go there. Go there in my mind. Uh-oh. What's going on with my iPad? Very sticky today. Maybe I just have clammy fingers or something. Okay, the probability of being uninsured, there it is. I'll grab it. So, okay, we're safe. Sorry. Little hiccup, but it might be the probability of being uninsured is 0.255, good. But we want 0 uninsured, which means that this one has to be insured, and this one has to be insured, and this one has to be insured. And so if I do 1 minus 0.255, then that gives me 0.745. So this one has to be insured, 0.745, 0.745. There. This one, and this one, and this one, and this one, and this one means I'm multiplying. Which is 0.745 to the power of 5, which is how we got here. I'm struggling with the wording. None uninsured. All insured? That makes more sense, I think. But technically true, but it's tripping me out. 0.745 to the power of 5, I guess, is 0.23. They probably did some rounding there. 1 minus that gives me the complement, right? So this is the probability of all of them being insured. So you can take that away, and then that's the from 1, and that's the probability that at least 1 is uninsured. So the probability of at least 1 is 1 minus the probability of none. We're going to use that trick again in chapter 4 quite a bit. And so we'll see it again, but nice to. Okay. Nice to have seen it. So roughly 20% of undergraduates at a university are vegetarian or vegan. What's the probability that among a random sample of 3 undergraduates, at least 1 is vegetarian or vegan? Right. First way you could solve this solve 2 ways. First way, you could find the probability of at least 1 is the probability of 1 plus the probability of 2 plus the probability of 3 vegans. Or the probability of at least 1 is the probability, or 1 minus the probability of 0. Right? Just take away the one that you don't want from the total sample space of 1. And then I'm going to do this one. What would I have to do to find each of these probabilities? Right? In each of these scenarios, I have 1 student, 2 student, 3 students. The probability of 1, it's actually more complicated, but one of the ways that I could have 1 is vegan, not vegan, not vegan, or I could have not vegan, vegan, not vegan, or I could have not vegan, not vegan, vegan. And I would need to figure out, so the probability of being vegan is 0.2 times 0.8 times 0.8, or 0.8 times 0.2 times 0.8, or adding these, right? Not vegan, 0.8 times 0.8 times 0.2. Again, these are what we call binomial probabilities because you're either vegan or you're not, right? And so we're gonna have shortcuts for doing these calculations. And by shortcuts, well, I guess you can look on your formula sheet. The binomial distribution is on there. It's on the in the next panel, right? And so we will see it because we do need to take into account that there are 3 different ways that I could order the vegans, right? Same thing here, right? I can rearrange them. So this might be a little bit easier. If I have to have 0 vegans, then I can think about first student, second student, third student. I'm forcing all of these to be not vegan, not vegan, not vegan. It's the only way that I could have 0 vegans, right? And these have a probability of 0.8, 0.8, 0.8. Which means that I have the probability of at least 1 is 1 minus 0.8 to the power of 3. Now you can look at the options and find that the last one is the one you wanted, right? Which is how I want you solving multiple choice problems, right? Any questions about that one?
Sorry, I missed. How did you get to 0.8 again?
Oh, the 0.8 is because the probability of being, whoops. Oh, cool. I didn't know I could do that. But that's not what I wanted to do. probability of being vegan is 0.2. So the probability by the complement of not vegan is 0.8. And then if it has to happen 3 times in a row, then it becomes 0.8 to the power of 3. Because I'm multiplying here to get that group. Any other questions? Then I think we're ready for conditional probability, which is the next section. Okay, so like I said, I'm gonna snag this part of our formula sheet, and we're gonna whittle it down to nothing. And I'll show you that you only need really one line here. So here, we've already done the independent events, so I'll kind of want to cross that out more. Huh? I usually only like to use this formula. Okay. We saw this last day, where if we have this vertical bar, we're going to read it as given. So the probability of A given B, we'll start down here, is the probability of A and B divided by the probability of B. Now, A and B are just placeholders, right? And so they could be a face card and a diamond. So what's the probability that I draw a diamond given that it was a face card? So I already know I have a face card. How do I find that? I know the probability of a diamond and a face card is 3/52. And I know the probability of a face card is 12/52. Right? And so then I can find the conditional probability. I got ahead of myself. We've got examples coming up. But so that's how we're going to use this formula. Why is this formula the same as this? Notice if we write it out, the probability of A and B is the probability of A given B times the probability of B. Well, if I solve for the probability of A and B, what would I do? I would divide both sides by the probability of B, right? And then I'll just switch these around the equal sign. That's okay. If A is equal to B, B is equal to A, that's allowed. So then I'm left with the probability of A given B is the probability of A and B divided by the probability of B. Now, of course, this is on your formula sheet, but it might be helpful to start thinking about, okay, if I have a conditional probability like this, the probability of A, so something given something else, you find the probability of them happening together, and then divide by the probability of the thing that's already happened, B, right? So the second part of this formula, right? You'll have the formula, but mapping the A's and the B's can be a little bit tricky, right? Especially if you do something weird, like what's the probability of picking a banana given that I already picked an apple? Uh-oh. The probability of a banana and an apple divided by the apple. Weird. You just gotta use those A's and B's as placeholders, right? And just whatever you use as A, just be consistent, and whatever you use as B, be consistent. This is the same, right? You don't actually need the second line, but the probability of A and B is the probability of B given A times the probability that A happened. right? Because now we're saying, okay, if the probability of B depends on what A did, then we need to incorporate that here. Yeah. We can also, okay, fine, I'll remove this. I'll redraw this line on here, but the probability of A given B, if the probability of A doesn't depend on B, right, that meant that those two things were independent of each other. So then the probability of A given B just becomes the probability of A, right? And that's how you have the probability of A times the probability of B. But I'll strike that out. Strike it from the record. So you really, if you're comfortable manipulating formulas like this, you really, I would say, only need this formula here. We really only need this formula. Now, for me, I'm the type of person who I only want to have the bare minimum on my formula sheet. But then there's the other extreme where they want to have all the derivations on your formula sheet. Now, I can do that myself, so I don't like to have those because I find that it gets really boggy. But I put them all on there because I want to be nice to the people who want all the derivations. But if you want, if you're like me, you can just ignore this part and just manipulate this function anytime that you have a conditional probability, right? And so this is what we call a conditional probability, probability of A, conditional on B happening. Okay. So what does it look like? Any questions before we start? We already started, I know. Before we continue. So I was reading my notes last night and I was, I meant to change this one because I can never, ever pronounce desipramine. Desipramine? Anyways, whatever. Doesn't matter. Researchers randomly assigned 72 chronic users of cocaine. I guess it's time to change this question anyways. Spicy. Into 3 groups. So desipramine, which is an antidepressant, I guess. Lithium, which is the standard treatment for cocaine, and a placebo. And the results of the study are shown below in this contingency table. So here we've got the treatment that they got, and here's the response that we saw. Looks like they were evenly distributed amongst the 3 treatment groups, which is pretty typical, right? 24 in each group, randomly assigned. Usually, pick a piece of paper out of a hat or something. No, I don't know. Usually it's double blind, so they don't know. But so we've got the 3 treatments, and then whether this patient relapsed probably within some amount of time, relapse yes or relapse no. Yeah. For simplicity, we can call this yes and we can call this no. Yeah. And then we'll remember that it's relapse yes, relapse no. Yeah. And we have 72 people in the study, right? And that's the grand total down here. So how many total relapsed? 48 out of 72, which means 24 didn't out of the 72, right? So we already know how to read this table. I think it spans a couple of, okay. What's the probability that a patient relapsed? So again, for simplicity, I'm gonna just call these yes and no, right? And so the probability of yes is 48 over 72. Huh? 48 over 72 is fine. It's a proportion, but that's roughly, okay, well, it's 2/3, but it's roughly 0.66. I'll do repeating. 7. So 67% of the sample relapsed. And so what we're doing is we're going to use the sample as a representation of the population. And then we can say that, okay, then the probability of relapse is going to be 67% or 0.67, right? That was a question hand. That's why I caught my eye. So far, so good, I think. Probability of relapse, we've got, okay, 0.67, so it's not looking good. What's the probability that a patient received the antidepressant and relapsed? Okay, so now they're on this antidepressant here and relapsed. Yeah. Let's call this, just for shorthand, D, L, and P. And for shorthand, yes and no belong to the response for the relapse. So what we want to find is the probability of D and yes. Probability, that doesn't look like a Y, does it? It's like a Yellowstone Y. There, that's a mathy Y. Okay. So they had to be on the antidepressant and relapse. So there's 10 of those. And the probability, the overall probability is 72, or out of 72. 10 over 72 is roughly 0.38 repeating. Or sorry, 0.138. Okay. You ready for a conditional probability? Oops. I have this on here. Hey. Okay, we're not ready. I'll put it on here. I'm gonna move this up here. Example, find the probability the patient was in the antidepressant group. Find the probability of a patient being in the diazepamine group, knowing that they relapsed. If we know they relapsed. So if we know that they relapsed, that's the same thing as given relapse yes, right? Which I'm shorthanding to y. So given y. So what I want to find is the probability of D given y. But from your formula sheet, like I said, as long as you map your A's and your B's consistently, right, then you can rewrite this as the probability of D and y. But usually how I just read it is I take this first one and the second one, and then I just divide by the probability of the second one, right? And that is the formula. So once you're more comfortable with it, that's probably what you'll do. Conveniently, we have these probabilities, right? We just found the probability of D and Y is, well, 10 over 72 or 0.138. And the probability of Y was 48 over 72 or 0.66 repeating. For a little bit of practice, should we use the fractions? Practice with fractions. So we have, this is the same as 10 over 72 divided by, and I'm trying to keep it on the same slide, 48 over 72. Of course, you're more than welcome to use your calculator and use the decimals. Try to keep as many decimal places as you can. In fact, try to store some values if you don't like working with fractions. But what we'll see is we get a really nice clean number here, because how do a fraction over a fraction, I have to flip the denominator and I have to multiply, right? We used to call it flip and kiss, but I guess we don't flip and multiply. It's cleaner. So 10 over 72, the numerator stays the same, but then the denominator times 48 over 72, and I always use my fingers so I can kind of watch them flip. It makes 72 over 48. 72 divided by 72 goes away, and I'm left with 10 over 48. Which is, roughly 0.20833. I'll sneak it on here. Oops, 3 repeating. Did you need the formula to find this? Not really, right? If you said, okay, what's the probability of a patient being in the desipramine group if we know that they relapsed? So we already know that they relapsed, which forces us to be in this group, which now has a total of 48 instead of 72, right? How many of those were in this desipramine group? Well, 10 out of 48. So you could have solved this with just the table, right? And that's totally fine, right? But there will be scenarios where you don't have a table, and then you'll need to use the formula, right? But in general, a lot of these questions, if you have a table, then you can just look at the table, and as long as you're kind of whittling down to the group that you're given, right, then you adjust your total and you know what to do. But those are conditional probabilities, right? Conditional that they relapsed. What's the probability that they were in the desipramine group? Okay. This has a lot of stuff on it. This is a different question. If you wanted to find the probability that they relapsed, knowing that they were in the desipramine group, right? Then I take the first thing and the second thing in the numerator, right? Relapse and desipramine, and then divide by the second thing, divided by the probability of the desipramine. I'm just running right through that word. Okay. Or what can you do? If I know that they were in this group, and I want to know what's the probability that they relapsed, that should put me at 10 over 24. Technically, what you are doing is this calculation, right? But from the table, you can just skip straight to here, right? Notice how those are two different questions, right? The probability that they relapsed, given that they were in the desipramine group, versus the probability that they were in the desipramine group, knowing that they relapsed, right? Two different things. Okay, we already did this one. And we already did this one, knowing that they relapsed. I'll just write down above, done earlier. Can do it. If we know that the patient relapsed, why not? Let's do it again. What's the probability that they received the antidepressant? So now we know that they relapsed, and we want to know 10 over 48. That's the one we did. That's kind of boring. We've got more fun things here. We can do the same thing for each of these groups. So we did this one, right? Knowing that they were in the antidepressant group, right? Or the probability that they were in the antidepressant group, knowing that they relapsed, 0.21, versus knowing that they relapsed, the probability that they were in the lithium group is 0.38. How would you say that these two treatments compare, right? Knowing that they relapsed, the probability that they were in the antidepressant group is 0.21. Knowing that they relapsed, the probability of being in the lithium group is higher, right? Worse treatment option, I think, if the goal is not relapsing. I don't know. Knowing that they relapsed, the probability of being in the placebo group is 0.42, the highest. So would you say from those probabilities, just your gut reaction, would you say relapsing is independent or dependent on the treatment? So consider the probabilities below. I'll say, would you guess, right? Just because we're just kind of developing that gut feeling. And so would you guess that relapse and treatment are independent or dependent what does it mean to be independent? It means knowing the outcome of one of the things. So knowing that they relapsed, if these things are independent of each other, then these probabilities should be roughly the same. Right? But because they're not, I would say it looks like the treatment and the relapse are dependent events. So here, since these probabilities are different from each other, I guess I should say, from each other, right? Relatively different, kind of a spread. We suspect treatment and relapse are dependent events. You'd be pretty bummed if you were doing this study and you found that all the probabilities were the same as the placebo, right? Nothing happened. Oh, better find some better treatment options, right? And so that's why we have the placebo there. Right. And so we're trying to find these dependent events, but we're going to have math to work through that to determine if they actually are independent or dependent, but we have to wait a few chapters until we can do that. So for now, we've got our guts. Guts. Well, any questions before we introduce a rule we've already seen? No. So the general multiplication rule is the rule that's on your formula sheet, and it says that, well, first, if two events are independent, we said the probability of A and B is the probability of A times the probability of B. But now, most of the time, and it's always safest to assume that they're not independent, right? Then the probability of A times the probability of B becomes the probability of A given B times the probability of B is the probability of A and B. So here I want to say, since the probability of A given B equals the probability of A if A and B are independent, right? I would encourage you to only use this formula, right? Because so many times I see people and they're just multiplying probabilities without knowing if they're independent or not, and that just doesn't work. Okay? So if A and B are independent, then the probability of A and B is the probability of A times the probability of B if they're independent, right? Because that probability of A given B, well, it doesn't care about B, so then it just is the probability of A. So you don't need that special case, just like you don't need the special case in the probability of A or B formula, right? Where you subtract the overlap. Well, if there is no overlap, you subtract 0, right? So, okay. If we have this hypothetical distribution of gender and major of students in an introductory stats class, what we've done is we've said, okay, you're either a social science major or you're not. We use that a lot, where we just make it binary, right? 0, 1, or yes, no situations by saying, well, you either are or you aren't. You are a social science major or you're not. We can do that, right? All the other majors get lumped into one. And so then we had females, males, and we had a total of 100 students. And so the probability that a randomly selected student is a social science major is, well, don't look at the answer, I guess, is a social science major, regardless of gender, is 60 over 100, so 0.6. The probability that a randomly selected student is a social science major, given that they are female, So now I know that they're female, so that makes my total now 50 instead of the 100, right? And then the probability of being a social science major is 30 over 50, which kind of confusingly is 0.6. I guess not really, because we're supposed to see that they're the same. Since the probability of being a social science major, given that they are male, is also 0.6. So knowing that they're male, the probability of being a social science major is still 30 over 50, a different 30 over 50, but still, right, is also 0.6. Then the major doesn't depend on the gender, right? Knowing the gender doesn't tell me the probability or it doesn't change the probability of being a social science major. So then that looks like this, right? Probability of being a social science major, given that they're female, well, it doesn't matter. It's just the probability of being a social science major, which was 60 over 100. Okay, I'm going to slide past this one because we have already talked about it a lot. Okay. So here are some probabilities that we're going to work with. So the American Cancer Society estimates that about 1.7% of women have breast cancer. And so here's our first probability. Feels disrespectful to say blah, blah, blah. Susan G. Komen for the Cure Foundation states that mammography, anyways, correctly identifies. Have you ever thought about when you say I edited it? I edited it. Anyways, kind of the same thing. Correctly identifies about 78% of women who truly have breast cancer. Okay? And so it's pretty low. Okay. So we're given this related information that we're going to use. Okay. Followed by an article published in 2003 suggests that up to 10% of all mammograms result in false positives for patients who do not have cancer. Okay. So a false positive for those who do not have cancer. Obviously, there's a footnote here that's worth mentioning that these percentages are approximate and very difficult to estimate, but these are our best guesses and might be outdated now, but still. Okay. Close your eyes. I need to take a sneak peek. Okay. No, that's the one I want to build. Okay. I'm going to add a page here. Because what we can do is we can build a tree diagram. So what's called a tree diagram is, have we seen a tree diagram yet? No, I don't think so, right? I usually save them for conditional probabilities. We can use them for unconditional probabilities before, but they're pretty boring. And so conditional probabilities, right, knowing the outcome of the first event determines the probability of the next thing. right? And so we use tree diagrams. And so we often use tree diagrams to visualize conditional probabilities. What they're going to look like generically is something like this. Most basic form of a tree diagram looks like this. And I do find in the textbook, they turn them kind of on their side for they're more readable that way. But I like to do them like this, kind of top to bottom, which is more of a root diagram, I guess, from the base of the tree going down. But still, I think you get the idea. Okay. So here, in this section here, we've got the first event. That event can be flipping a coin, right? You flip heads, you flip tails. You can only go down one of those paths, but they can both happen. Now, the second set of branches is the second event. Flipping a coin would be pretty boring, right? But you can figure out, okay, heads, tails, and then I could flip again, heads, tails, heads, tails. Okay. Those are independent events. So it's, again, pretty boring. So for example, flip a coin, oops, Philippe. Flip a coin twice. Heads, we can get tails, we can get heads, we can get tails, we can get heads, we can get tails. This gives me all the possible outcomes, right? A way to visualize all the possible outcomes. Now, usually at the bottom, I like to summarize what the events that happened. So at the bottom of this branch, I flipped heads and I flipped heads. So I'm just going to shorthand this. Well, H and H, but I just write it as HH. I ditched the end. So here, the next option would be I flipped a heads and then I flipped a tail, head, tail. Flipped a tail, whoops. Then I flipped heads, or flipped a tail, then a tail. So tail, head, tail, tail. Notice now I have what? I have my sample space of all possible outcomes, right? And so, right, this is my sample space, HH, HT, TH, TT, from flipping a coin twice. Okay. So this is my sample space, S. All possible outcomes. What's more useful is if we attach probabilities to these things. Now, again, this is pretty boring, right? But the probability of H is 0.5, probability of tails is 0.5, 0.5, 0.5, 0.5, 0.5. We know what's the probability of HH. Well, we could say, okay, that's the same thing as a heads and a heads, right? 0.5 times 0.5. But really what we're doing when we're using this tree is we would multiply down the branch to find the probability of HH, probability of HT, probability of TH, probability of TT. So we can jot those down. Probability of HH is 0.5 times 0.5. Probability of HT is 0.5 times 0.5. And try to stagger them here. TH, surprise, 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 surprise. 5 times 0.5. That's all boring. Why is it boring? Well, they're all the same for one, but technically what we're doing here, and let's see if there's a color I can use, purple maybe. Technically, this is the probability of H given H. Knowing that I flipped heads earlier, what's the probability of another H? Well, it's 0.5. That's why it's boring. That's going to change, right? Knowing that, okay, you have cancer, then what's the probability of testing positive, right? Knowing that you don't have cancer, what's the probability of testing positive, right? So those are conditional probabilities, and that's when it comes into play, right? But technically, these are the probabilities of T given H. Right. But in the end, to find the probabilities at the end of all these branches, you just multiply down. 0.5 times 0.5 is 0.25, so a quarter plus a quarter plus a quarter plus a quarter. Adding up the probabilities in the sample space must equal 1. Must be 1, since the probability of the sample space must be 1. Right? So that's one thing that you can use to check. Make sure that they all add to 1 once you add them all together. Okay. We ready to map the previous information into a tree diagram? Well, whether you're ready or not, here we go. So now, we will map the previous information. The first branch is going to be the cancer branch. Now, in this case, I'm telling you, but on the test, you'll have to figure out which one is your first branch and which one is your second branch. Okay, and so I want to give you the reason, or I want to show you the reason we're told that 1.7% of women have breast cancer. Okay, so that's going to be a probability at the top of our branches. Now, the reason it's at the top is because knowing that someone has breast cancer, then the probability that the test correctly identifies it is 0.78. Okay. And so what we're going to say is that here, the probability of cancer is 0.017. Now, the probability, I want to use a positive test because, well, one, I know it's coming, and two, I want to have kind of some overarching outcome, right? Instead of talking about correctly identifying if you have cancer. So when you say if you have cancer, that's a conditional probability. And so what we're going to say is we're going to say the probability of a positive, knowing that they have cancer, so given the given C, is 0.78. It's not stated, but from there, you could tell me, well, then what's the probability of a negative result knowing that they have cancer, right? So if you just read this, mammography correctly identifies about 78% of women who truly have breast cancer, meaning it incorrectly identifies 1 minus 0.78. right? And so that's the complement. 1 minus 0.78, which puts me at, I've got a cheat sheet here, 0.22. And then I confirm instead of doing the math. Okay. So here, the last bit of information is, okay, if I know that someone does not have cancer, the probability of a false positive or a testing positive, right, because it should be negative, is 0.1, right? And so here, what we're going to call this is the probability of a positive given how about that? Not cancer. The complement of cancer. Uh-oh. As often as possible, I want to talk in binary, right? Yes, no, right? Because otherwise it gets overwhelming with the number of branches that you have to think about. Okay? And so you either have cancer or you don't. Right? So not cancer, the complement of cancer is 0.1, which means that if you test, the probability of testing negative, knowing that you do not have cancer, must be 0.9, 0.90. Okay. So because this information here all hinged on, well, did they have cancer or did they not have cancer? That means that, okay, the first set of branches that I need to map out is, well, do they have cancer or not? Because that's going to determine the next conditional probabilities. Okay. Maybe I'll try to, I'll just snag a mini copy of this so I can refer to it. Copy. And paste it real small. For my eyes only, I guess. No, but then I don't have to scroll around so much. All right, so that's what we just did. And so this is what tells me that, okay, cancer or not cancer, my first set of branches. Yeah. Below, we can write the probabilities. Yeah. The probability of cancer, we were told, was 0.017. Make that more obvious. Which means that the probability of not cancer, just scooch this a little bit. The probability of not cancer is 1 minus 0.017, which I'm going to go with 0.983. Either you do or you don't. Good. That's the first kind of part of our decision tree or decision roots. I've never realized that it's not a tree. Well, it's an upside down tree, I guess. My next set of branches, whether this patient has cancer or doesn't, they can test positive or not. Now, if you prefer, you could say, or the complement of plus, but I find that negative might be a little bit easier, right? Because it's only one stroke instead of 3, right? But it is the complement of positive. And if you don't have cancer, you can still test positive or you can test negative. So now, right, I have all the possible outcomes here, which I can list at the bottom. Patient can have cancer and test positive, can have cancer and test negative, cannot have cancer and test positive, and cannot have cancer and test negative. Those are all the possible outcomes. All right. I think we're all convinced. There we go. Bless you. Now, we were given that the probability of testing positive, given that they came down the cancer branch, right? Which is nice because that's the only information that we have, right? We don't have the probability of testing positive yet. We have to find it overall. And so the probability of testing positive, given that they have cancer, we were told was 0.78. Can I maybe scooch this a little bit? There. So that's from here. So testing positive, if they have cancer, the probability of that is 0.78, which means testing negative, even if they have cancer, is 0.22. That's pretty bad. Probability of testing negative, given that they have cancer, is 0.22. If they don't have cancer, the probability that they test positive is 10% or 0.1. So the probability of testing positive, given that they don't have cancer, is 0.10. Which means that the probability that they test negative, given that they don't have cancer, is 0.9. Now we know from math and what we just saw, and I'm just going to focus on this guy here, the probability of C and positive, right, is the probability of C, or in this case, sorry, positive given C times the probability of C, which is really just this times this. Wait, not in pointer mode. Right. So to find the and probabilities, right, you don't need to work with the formula anymore, because what you're going to do is, if both of these have to happen, this and this, then you multiply down the branches, right? And so here I'm going to write or simply multiply down the branch. Then the probability of C and plus, so C and positive, is going to be 0.017 times 0.78. Okay. So then the probability of C, and I'm ditching the and. If I just smush them together, I can read it as and, is 0.017 times 0.78. Which puts me at 0.01326. So usually what I do is I don't worry too much about kind of the formula behind the branches, as long as I know, okay, if I'm multiplying down the branch, then at the end of the branch, I'm finding the probability of the first thing and the second thing, right? Which is why I've summarized the combinations down below. So usually what I do is I just jot down, I just multiply down all the branches right away. Why do I do that? Well, it's tedious and I like to do tedious things, but also then I can double check that I did it right by adding them all up and making sure they add to 1, right? Because otherwise I might have got some numbers wrong. So usually what I do is I'll just write 0.01326. Careful you don't do much rounding, right? Because you have to add them to 1. Now in this case, it gives us a nice kind of reasonable number, and so I'm going to keep them all, of course. What's the probability of a patient having cancer and testing negative? 0.017 times 0.22. Right? So 0.017 times 0.22 puts me at 0.00374. Now it gives me or scientific notation. So 1, 2, 3. Okay, good. What's the probability of a patient not having cancer and testing positive? Right, so this is just overall. 0.983 times 0.1 puts me at 0.0983. And then finally, what's the probability of a patient who doesn't have cancer testing negative is going to be 0.983 times 0.9, which is a nice high number, I think, 0.8847. Adding these all up, right? Plus, plus, plus. I should get 1, but I'll confirm. Plus 0.0983 plus 0.00374 plus 0.01326. Whew. Get myself a green check mark. Right? So that's how I can double check that all my numbers that I had work. Yeah. Good. Notice that these branches add to 1, these branches add to 1, and these branches add to 1, right? Or those probabilities, rather. Okay. We can use this to find probabilities. What if I asked you, what's the probability of testing positive? Right? We don't know whether they have cancer or not. It's not a conditional probability anymore. We look at this and we see, okay, there's actually 2 ways that I can test positive, right? I can have cancer and test positive, or I could not have cancer and test positive, right? So when you're saying or, you can add those probabilities, right? And so if you're interested in more than one branch, you can add the probabilities at the end of each branch, okay, to find that total probability. How much space do I have here? I know it's coming up on a future slide, so I'm just seeing, okay. The probability of testing positive is the probability of having cancer and testing positive plus the probability of not cancer and testing positive. Right? Notice that here we're saying or. But we already have all those probabilities at the end of each branch. And so now I have the probability of C and positive is 0.01326. And the probability of not having cancer and testing positive is 0.0983. Which means 0.01326 plus 0.0983. I get 0.11156. So the probability of testing positive, right, which is usually from where we're coming from, right, is 0.11156, right, or 11 point some odd percent. Good. So we can add, or maybe I'll say here, testing positive happens in 2 branches. So we can add the probabilities at the end of the branches. It is in the slides, but since I said it, I want to write it down. Okay. So now we can use this tree, right? So when a patient goes through breast cancer screening, there are 2 competing claims. The patient had cancer and the patient doesn't have cancer. And if a mammogram yields a positive result, right? So here, conditional on a positive result, what's the probability that they actually have cancer? And so what we need to do first is we need to say, okay, I need to find the probability of cancer knowing that there was a positive result. So being comfortable with the conditional probability, right? We can read this as, okay, I can rewrite this as the probability of C and positive divided by the probability of positive, right? Or you can use your formula sheet. That's fine too. We have all this information, right? The probability of C and plus, so cancer and positive, we know is 0.01326. So I'm going to jot that down. And we also did all that work for finding the probability of it being positive. Otherwise, we would have to do that here, right? But we already found that, okay, there are 2 ways that I could test positive, right? And so this or this, whoops, or this. So I added those probabilities together. And I found 0.11156. The previous page, because we did a lot of work there. So now 0.01326, now it's just math, divided by 0.1, did zeros, 11156. I get 0.118859864, because I don't know when to stop. That's okay. Which means that the probability that they have cancer, given that it was a positive result, is 11.89%, right? Or 0.1189. So here, these next few slides are just a typed out version of what we did together. Okay. So, and again, they like to turn it on its side, and I get it, because then you can read it just normally, right? But at the end of each of the branches, you multiply the probabilities. We wrote out a lot more than this, but this is really just the information that you need, right? So I usually drop the conditional probability notation, and I just remember that, okay, that branch is conditional on the previous branch, right? What about this one? Suppose a woman who gets tested once and obtains a positive result wants to get tested again. In the second test, what should we assume the probability of this specific woman having cancer is? So now the probability of it being cancer on the second test has to be the probability of cancer given that it was a positive result, which is what we just found, right? And we said it was 0.1188598064 from earlier, which we can round to 0.12, right? Or roughly 0.12. So now in the second test, right, that alters the probability of having cancer because we already know that there was a positive result. Okay. Let me just have a look here. Well, first, sorry, any questions about this one? Hey, okay. No, you know what? We're doing all right. This is hard stuff, right? But with the tree, it makes it a little bit easier at least. How about this one? What's the probability that this woman has cancer if the second mammogram also yields a positive result? We're going to need to make a new tree, right? We'll be quicker this time. For this particular woman who's already had a positive result, altering the probability of cancer, right? Upping it, let's keep it at 0.12, right? That's nice and round here. So 0.12, or sorry, I grabbed the wrong thing. Notice how sloppy I am? I'm not even writing the probability of C is 0.12. I just jot down the probability below. We're gonna get lazy with this stuff. What's the probability of not cancer then? Must be what, 0.88? You thought that was lazy, not writing out the probabilities. You won't believe what happens next. positive, negative, positive, negative. Right? Those are the outcomes. And so now, these probabilities don't change, right? And so the probability of testing positive, given that they have cancer, is still 0.78, right? And so the test results, those probabilities stay the same. So I'm going to snag those from earlier. So the probability of testing positive if they have cancer was 0.78. I'm not even writing down the conditional. I'll do it for this one. Maybe I'll change it to like ghost writing style. There. Ghosts of notation past. How about this one? This is technically the probability of a positive given cancer, but again, I'll do it in ghost style. Because I don't even write it anymore. Okay. So then we know here if the probability of a positive is 0.78, the probability of a negative is 0.22. Probability of a positive if they don't have cancer was 0.1, and probability of a negative then if they don't have cancer was still 0.9. So these probabilities don't change. Whoa. These probabilities didn't change, but these ones changed, which will change all our math, right? All our multiplication. So what are we trying to find here? We want to find the probability of cancer given another positive result. Which is the same thing as the probability of C and plus divided by the probability of plus. We already did that math once, but let's do it again with different numbers, right? Because we've altered the probability of this person having cancer. Yeah. Again, I'm going to multiply down all these branches. I don't need all these branches. In fact, I only need 2 of them, right? But I don't know that. And usually it's multiple parts, and you may as well just do it while you're on a roll, right? So at the bottom of each of these branches, I do like to put a summary of what is at each branch: C plus, C minus, C complement plus, complement of C minus. And these probabilities now are 0.12 times 0.78, which is 0.0936. 0.12 times 0.22 is 0.0264. 0.88 times 0.1 is 0.088. And 0.88 times 0.9 is 0.792. I can't resist. Let's add them up. It just feels so good when they equal 1. 0.0264 plus 0.0936. And also I want to catch any problems, right? If they don't add to 1, I have to adjust my numbers. Something went wrong. Usually you're just missing a 0 somewhere, or added a 0 somewhere, right? So this is a nice double check to have. Okay. So now, if we want to solve for the probability of cancer given a positive test, now remember this is the second test, is the probability of C and plus divided by the probability of plus. we've got the numerator fine, right? C and a positive is 0.0936. But the positive happens down this branch, but also down this branch. It's the same thing that we did earlier, but it doesn't hurt to see it again, right? And so this branch or this branch is the probability of a positive, right? And so what we're going to do is divide this by 0.0936 plus 0.088. So not C and positive. My arrows should probably keep going. There. It might be tempting to say, well, this is already here and this is here, and why don't these cancel? Wow, no, that's illegal math. You can only cancel if you've got a common multiple, right? But here you're adding in the denominator. And so you're gonna combine those 0.0936 plus 0.088, and we get 0.0936. It's gonna span a page here. That is not fun. How about this? Divided by 0.1816, which is 0.5154185022. Or roughly, what were the options? 0.52. That's some nasty rounding. Oh, no, it's not. Fives. I didn't want to see this 5. So 4. It's good rounding. It's fine. 0.52, which means a lot of work went into that multiple choice question. Man. So now the scenario is what? A woman went and got tested positive, then tested positive again. What's the probability that she has cancer? 52%, 0.5. Still kind of low. I think, yeah.
We're in a test, we get like a question, say like this. How much of it is going to be based off of the actual like A, B, C, or D versus like work shown to get to that test?
Usually for this type of big question, I wouldn't give you a multiple, it wouldn't be a multiple choice. I would just want to see your process. So for me, I emphasize the process a lot, right? And so, which is why it takes me forever to do my marking, because I have to get in all your brains and try to figure out, okay, what happened here? And so I'm usually not looking for the right answer. Obviously that makes it easier, but it's all about procedure. And so the more that you can show me that you know, the better. And so I would start off and ask you to draw the tree diagram, right? Fill in the probabilities, that's worth something, and then answer some questions about it using the tree diagram. But that's good. And then let's skip Bayes' theorem, but we'll start off with this activity on Thursday. If you have any questions, let me know. Otherwise, I'll see you then.